Hi all, welcome to this talk. So I'm going to talk about optimal tiling of Euclidean space using symmetric parties. This is joint work with Mark Performan, so let's go. So before I talk about anything in the title, let me give you some background about the problem and motivation for it. So this all starts with the PCB theorem, and in order to introduce that, let me define the label cover problem. So an instance of label cover is composed of a bipartite graph G and two finite alphabets sigma n and sigma r, one for each side of the graph, along with a constraint, one for each edge of the graph. So a constraint is simply a collection of tuples of labels that are considered satisfactory, and the goal in the problem is to find labelings of the vertices that satisfy as many of the constraints as possible. So label cover is a very general problem, and you can formulate many optimization problems using that. For example, max cut, max two-sat, tooling, and so on. Also, using label cover, you can formulate the PCB theorem as follows. So the theorem asserts that there exists an absolute constant delta less than 1, as well as an integer k, such that if I give you a label cover instance psi with alphabet sizes at most k, it's NPR to distinguish between the cases that you can satisfy all of the constraints of psi and the case you can satisfy at most delta fraction of the constraints of psi. So this theorem is really great. You can do many things with that. You can prove many harness of approximation results. However, most of them will be quantitatively weak. And if you want to prove better harness results, you need to improve upon this theorem. And there are two ways in which you can try to improve on that. First, you can try to get better soundness guarantee. Namely, you can try to get delta B to be smaller. And secondly, you can hope to get more structure out of your label cover instance. Most prominently, you can try to get more structured constraints. So this is something, both of these improvements are something that people study, but for us today, we'll focus on improving the soundness. This is the main question we'll be concerned with. And the way to do that is using what is called soundness amplification. So what is soundness amplification? So to motivate that, let me switch to a completely equivalent question, yet it's a bit easier to think about, at least for our purposes. So this is a language that is called two-prover one-round games, and it goes as follows. So suppose we have psi, which is a label cover instance, and we have a verifier, which is computationally bounded, trying to understand whether this psi is highly satisfiable or not. And to aid him, there are two provers that are not communicating, and the verifier is allowed to ask them questions, and they give him answers. So how would the verifier check whether this label cover instance is highly satisfiable or not? Well, what the verifier is going to do is it's going to pick an edge, it's going to pick a challenge, uniformly at random from the graph. It's going to send one endpoint to each one of the provers. Each prover will provide him with a label. And then what the verifier is going to do is check whether the labels that the provers gave him satisfy the constraints. It's easy to see that the best strategy for the provers, the probability that the verifier would accept in that is exactly the maximum fraction of constraints that can be satisfied in the label cover problem. So this problem is completely equivalent to satisfying as many constraints as possible. And we'll use this formulation to think about this problem. So how do we make the gap larger? How do we identify whether this label cover instance is highly satisfiable or not with more certainty? Well, this is what parallel repetition is for. So what is parallel repetition? So now instead of sampling a single challenge, the verifier is going to sample t challenges, where t is something larger than 1. It's free for you to choose. Is going to send the left endpoints to prover 1, the right endpoints to prove or to is one bunch of questions. And as before, is going to get a label for each one of the vertices that is sent to each one of the provers. And then obviously, what the verifier is going to do is going to check that all of the challenges that he picked are satisfied by these labels. So it's easy to see that if we start from a highly satisfiable level cover instance, then when you do this default repetition, you end up with a highly satisfiable level cover instance as well. Namely, the value of this default repetition is at least 1 minus epsilon to the t. And the proof is clear. There is really nothing to prove here. It's obvious you execute the same strategy on each coordinate. But what about the other direction? So suppose our level cover instance was not highly satisfiable. What can we say about the default repetition? How much harder is it? So I claim that it's completely clear that if your original value is most 1 minus epsilon prime, then the value of the default repetition is most 1 minus epsilon prime to the t. Right, because the first coordinate you win with only 1 minus epsilon prime, the second one is independent of the first, so you also get 1 minus epsilon prime, and so on and so forth. So the proof is clear, right? Well, but is it clear? So what I said is, of course, a lie. It doesn't really work like that. And not only is this proof not clear, this statement is actually false. And we'll get down to this business very soon, but this is where the business of parallel repetition really starts being more difficult. So what can we say about parallel repetition despite this difficulty? So for technical reasons, I'm going to focus on what is called projection games. The definition is on the slide, but don't worry about it too much. This is kind of the type of games we mostly care about in hardest approximation. So how good is parallel repetition? Namely, suppose I tell you that I have a label cover instance whose value is most 1 minus epsilon. What can you tell me about the value of the default repetition? So the first result along these lines was proved by Verbitsky, who proved that this value at least tends to 0 as t goes to infinity. So the bound that he gets are not the best, because the argument is some Ramsey type argument. So you don't get something that is impressive quantitatively, but at least in something. And the really strong quantitative bound was proved by Iran Raz a bit after that, who proved that the value indeed drops exponentially in t, but not in a straightforward manner. So he proved that the value of the default repetition is at most 1 minus epsilon to the 32 to the t. So this is a really nice theorem and a really good bound, but this leaves some much room for improvement. And indeed, following Graz's work, Holenstein improved upon this bound to improve the epsilon to the 32 to epsilon to the 3. And later on, Rao proved this further down to epsilon squared. So this is nice and all, but still the question remains, does strong parallel repetition hold? So formally speaking, strong parallel repetition asserts that we could replace this epsilon squared with something linear in epsilon. But in reality, if you manage to improve this epsilon squared to anything better, like epsilon to the 0.1999, that will still be considered strong. And the main reason for that is if we manage to prove any such strengthening of parallel repetition, it would be really very, very nice in terms of complexity theoretic applications. So I'm going to soon describe these applications, but this is what strong parallel repetition is mostly about. Good. And we'll also see later on in this talk and that this type of questions are related to very interesting geometric problems about tilings of Euclidean space. So why should we care about this strong parallel repetition? Why do we need to get this epsilon squared down further? So this is a tale of two conjectures. One of them is the Uniqueness conjecture. So this conjecture is a conjecture about the complexity of solving a very structured linear system of equations over a finite field. So you are given a system of linear equations, in which each equation is composed of two variables, and you ask whether this system of equations is almost satisfiable or whether it's only very poorly can be satisfied. And the conjecture made by Cort is that for every epsilon greater than 0, if you take a large enough field, it's simpler to tell whether a given system of just equations is at least one of its epsilon satisfiable or at most epsilon satisfiable. So this is, of course, a very natural question about the complexity of linear equations, but the reason that it's so important is because if you manage to prove this conjecture, you get for free lots of implications. You get to know a lot of tight approximation results, and this is something that we want to prove very, very much. So this is the first conjecture. In contrast to that, we have what is called the max-cut conjecture. So what is max-cut? You have a graph G, and you want to partition the vertices into two sides, L and R, so that as many edges cross from one side to another. So in this language, the max-cut conjecture asserts that if epsilon is small enough, it's NPR to tell, given a graph, whether you can cut at least 1 minus epsilon fraction of the edges, or you can cut at most 1 minus 2 over pi times square root of epsilon, plus some error term, a fraction of the edges. In other words, this conjecture asserts that the Gomans-Williamson algorithm for max-cut is optimal. So we have these two conjectures, and we ask about relations between them. More precisely, we ask, does the max-cut conjecture imply UGC? If so, that would be a very promising avenue towards unique games, because max-cut, the gap seems to be fairly modest. So this is a gap between minus epsilon and minus square root of epsilon. So it seems like something that maybe we can prove one day, whereas in unique games, the gap is very large. So it seems sensible that perhaps for max-cut this would be simpler. And the question that you ask is, would it then imply unique games as in a black box manner? And this is where strong parallel repetition enters the picture. If we had strong parallel repetition, we would be able to say that this deduction would follow in a black box manner. And moreover, the quadratic gap that we had in the slide before is exactly this gap between epsilon and square root of epsilon that we have in the max-cut conjecture. So because we have this epsilon loss, the gap disappears, but if we had something less than square, we'd have it. So this is one of the primary motivations to study, or perhaps the primary motivation to study strong parallel repetition. So this is it. And I should mention that the other direction is known. It's known that the Uniqueness conjecture does imply the max-cut conjecture. So in actuality, what we're asking here is whether these two conjectures are equivalent or not. Good. So with this motivation out of the way, let me tell you what we're going to see in this talk. So we're first going to discuss some complications in the study of strong parallel repetition. In particular, I'm going to show you an example showing that strong parallel repetition fails due to unhas. This is called the odd cycle game. I'm going to tell you relations of this problem to Tylik problems, as well as variations on parallel repetition. And then I'm going to tell you how efficient tilings relate to good strategies in this game. And finally, I'm going to tell you about symmetric parallel repetition and our results. And in the end, I'm going to mention some open problems that we think are interesting. Good. So as I said, people were really interested in strong parallel repetition and thought that this is a promising avenue in complexity until Raz came and showed that it fails. So Raz showed that there exists a very simple game, a max-cut instance, its value is minus epsilon. Yet, when you do t for the repetitions, this epsilon only multiplies by square root of t. instead of t, which is what strong parallel repetition would predict. And what's cool is that this game is very, very simple. It's nothing complex. So the game is as follows. You have a graph, which is an odd cycle. The labels are 0 and 1. And the constraint on each edge is that the labels that the endpoints of the edge receive are different. In other words, what you want to do is partition the vertices of the graph into two sides so that as many edges cross from one side to another. So clearly, because this is an odd cycle, it's not a bipartite graph. So whatever bipartition you choose, you have to miss at least one edge. So this is why the value of this game is 1 minus 1 over n. This is easy to show. However, what is harder, and this is what Raz proved, is that if you take t-fold repetitions of this game, the value is 1 minus square root of t over n, as opposed to 1 minus t over n, which would be what you naively expect. So this is kind of discouraging from complexity point of view. This seems to kill the strong parallel attempts. And yeah, indeed, this is kind of discouraging, but still one can look at variations of parallel and maybe some other ideas in order to try to remedy the situation. And this is indeed what people did. So people considered some variants of parallel repetition as well as some special classes of graphs in the hope that maybe this will be enough to show this connection between the max-cut conjecture and UGC. So some special classes of graphs have been studied, such as expanded graphs, and indeed there you do have strong parallel repetition. So people also suggested some other operations of graphs, most notably the operation called fortification, which is good because you get strong parallel repetition with good bounds and even simple proofs. But the main drawback here is that it kills the uniqueness of the game, so it's not really applicable as far as the connection that I mentioned is concerned. And finally, there is this variant which is called symmetric parallel repetition, which is very interesting, but it's mysterious. It's not clear what it does. And the main motivation for our work was to try to begin to understand this symmetric variant of parallel repetition. More precisely, what we do is we try to understand what happens in the odd cycle game of Raz under symmetric parallel repetition. And to be more precise, what we do is we study a geometric tiling problem that is very much related to it. We get a tight bound for that, and then we derive some corollaries for the odd cycle game of Raz. So next, I'm going to describe this tiling problem and tell you how this is related to the study of parallel repetition. So good, so let's begin with a quick definition. So let n be large. We say that a body D in Euclidean space is tiling if, first of all, when you look at the integer shifts of this body, they cover the entire Euclidean space Rn. And secondly, these integer shifts are mutually disjoint. So this is the picture you should have in mind. And here are some examples for tiling bodies. So clearly, one thing you can do is simply take a cube, 0, 1 to the n. This is clearly tiling. But then you can try to play around with that. You can give it angles everywhere and call it a biped. And this would also be tiling. And the key parameter of interest that turns out with respect to parallel repetition is the surface area of a tiling body. So the above two examples both have surface area which is linear in n, and the question is, can we beat it? So let's first observe that the surface area of any tiling body must be at least square root of n. And what is the proof? Well, it's easy to see that if D is tiling, the volume of D must be 1, because you have to cover Euclidean space by each of the shifts. But then, among all bodies with volume 1, the one that minimizes surface area is the ball, and a ball is square root of n surface area. So this is why your body must have surface area at least square root of n. So we have a lower bound of square root of n, we have an upper bound of n, and it's not clear what is the answer. And perhaps intuitively, you think first that probably the answer should be closer to n, because what is square root of n? It's like a ball, so a ball is not tiling, right? It's very far from it. But the answer is somewhere in between, it's not completely obvious. So there are 3 questions you must ask. What is the answer to this question? How is this relevant at all to parallel prediction? And thirdly, how does symmetry enter the picture? Well, let me first begin by describing the relevance to parallel repetition. So the connection that I'm going to show now is from a work by Fege et al., and it goes as follows. So what is this really odd cycle when you take t many repetitions? So this is really a discrete version of the torus, the t-dimensional torus. Right, because the cycle is something that goes like that, but in discrete steps, and the torus is something that goes like that, but in continuous steps. So it's really the same thing up to discretization. And what we want to do is remove a least number of edges from the torus or from this product graph and eliminate all non-trivial cycles. That is, cycles that wrap around non-trivial. So how is this related to tilings? Well, in order to see this connection, let's look at the torus and unwrap it. Let's look at a two-dimensional view. So this is a two-dimensional drawing of a t-dimensional torus. Of course, it's not going to work, but you know, this is not the way to do it because the top is the same as the bottom and the right is the same as the left. So it's convenient to think about it in this way. So what is a non-trivial cycle in this drawing? So it's some cycle that starts at some point described by this O. It goes in some direction, let's say up. It goes up, 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 until it hits the top, but top is same as bottom, so it wraps around, goes, and then it finishes the cycle. So what we want to do is we want to eliminate all of these cycles. And here there is one very crucial observation. If you look at such cycle, what you end up doing is you take a point, you go all of these steps, and eventually what you do is you really add up an integer because all of this work ends up adding 1 in one direction and 0 in the rest. So this is an integer shift. And what do we know about tiles? We know that if I look at an x and I take an integer shift of x, then the shift cannot be in the same tile as x. In other words, such cycle cannot be contained in a single tile. And once you see that, it starts making sense that this tiling business is related to removing cycles from the torus. How? Well, what you do is you simply take your tiling and you put it on the torus. So you put it here, there, put it everywhere. And what you do then is you remove all edges of the torus that go from one tile to another. So by the earlier observation, this removes all of the non-trivial cycles from the torus. And the question is, how many edges did we remove when we did this? So we removed edges that escape from a given tile. And this fraction of edges is precisely what is captured by surface area. Surface area really measures the escape probability from a body in small steps. So this is why we want to minimize surface area of tiling if we want to get good strategy for the odd cycle gain. And when you take repetitions of it. So this is a very nice connection. And following this discovery of this connection, Ramraz actually showed his odd cycle game and proved that indeed you have surprising strategy for that. And following Raz's work, Kinder, Rao, Donald Vigdorson managed to construct a tiling body that has a very small surface area close to a ball, namely O of square root of n. This was later made more explicit by Adlon and Clark. So the question that we ask ourselves in this work is, what about symmetric permutation of the odd cycle game? How does this perform, and how is the related tiling question solved? So next up, I'm going to talk about symmetric tilings for green space, symmetric repetitions, and our main results. So what is symmetric parallel repetition? Well, it's very similar to parallel repetition. Again, you have your verifier. He wants to verify that the instance is highly satisfiable. But now, instead of picking challenges and sending them as tuples, what the verifier is going to do is pick challenges and send the endpoints to the prover 1 and prover 2 as unordered tuples. Or said it otherwise, is going to send the challenges to the provers as sets. So again, the verifier expects to get a label for each one of the vertices that send to each one of the provers, and is going to check whether these labels satisfy all of the challenges that he has in mind. So here are main theorems with regards to parallel repetition. So we prove that for the odd cycle game, as long as you don't have too many repetitions, when you make t for repetitions, the value of the game drops like 1 minus t over n square root of log t, which is much better than what ordinary parallel repetition gives you, which is 1 minus square root of t over n. So this is nice, but still you have this annoying square root of log t factor, which you may not originally expect. Secondly, what we show is that square root of log t is necessary. We show that even for symmetric repetition, you still have some surprising strategies in the odd cycle game. So the good thing about this result is that this is a very strong amplification rate, and if you manage to prove something like that for a rich enough class of games, you'd have this connection between unique games and max-cut conduction. The bad thing is that we only proved it for a very specific game, for the odd cycle game, and we know that in general this cannot hold. But perhaps we can combine this idea with other ideas and add it to our toolbox that eventually will establish this connection between max-cut and unique games. This is one step along this direction. So how do we prove these theorems? Well, as kind of before, what we do is we move to a cleaner space. We consider a continuous version of this problem, which turns out to be the tiling problem for permutation-symmetric bodies. And we give asymptotically tight bounds for this problem. And then we show that you can discretize this proof and make it go through even in the odd cycle world in order to prove these two results. So what are symmetric tilings? Well, again, it's very similar to tilings. Body D is called a symmetric tiling. First of all, it is tiling. And secondly, it is symmetric with respect to the action of Sn, meaning point X is in D if and only if, however you permute the coordinates of D, of X, it remains in D. So an example is simply the cube, 0, 1 to the n. And again, the question is, what is the less surface area a symmetric tiling body has? Again, we have the trivial upper bound of n, and the question is, can you build it? So we prove two results. We prove that, first of all, any symmetric tiling body must have surface area at least n over square root of log n. So this means that you are very close to a cube, but still it's not quite linear in n. And secondly, we prove that this is the best possible, meaning there are in fact tiling bodies that achieve this boundary. Namely, still the answer even in the symmetric case is not n. There are bodies with surface area at most n over square root of log n. Good. So let me finish this talk with some open problems. So first of all, it would be very interesting mathematically to study the styling body for other classes of bodies. For example, convex bodies, something that comes to mind as natural candidate. Namely, are there any non-trivial tiling bodies that are convex? We don't know that. So this is an interesting question mathematically, but we don't know of any complexity motivation for it. Secondly, we can ask for more generic procedures for amplifying harness, because it would be very nice to sort of build up our arsenal in order to maybe eventually prove this max cut versus UG connection. And thirdly, in the case of unique games at least, in repetition, there is a very nice characterization of this kind of amortized value of a game, which is kind of the value of n-fold repetitions when you take a log and divide it by n. So it's kind of an amortized sense. So it would be interesting if there is any nice characterization of that for symmetric repetition, even for special classes of games such as unique games. So I hope you enjoyed the talk, and I thank you very much for listening.